Hyperbolic paraboloid. Okay, so the oid is attached to the parabo part, so you can expect two traces to be parabolas. And then one of the traces is going to be a hyperbola. Now, when I say one of the traces, I mean one of the possible kinds of traces. There'll be an infinite number of traces that are hyperbolas, but they'll all come from cutting it with, say, a horizontal plane. So what does this thing look like? Well, using the right perspective, it kind of looks like a saddle shape or a Pringles potato chip. So how could you draw this? This is another one where you want to draw it freehand. So one trace will be a parabola opening down. And when I say one trace, one kind of trace is what I really mean. So I'm going to draw I've drawn two parabolas opening down. That's one kind of trace that you'd get by cutting this thing with a vertical plane. And so that's one type of trace you'd get, one of the parabolas you'd get. Another parabola you're going to get is if you cut it, like say with the XZ plane, you'll get a parabola that opens up this time. And then if you cut it with a horizontal plane, parallel to the XY plane, the traces will be a couple of hyperbolas. There's one, and here's another one. And so if you use your imagination, that kind of looks like a saddle. The vertex will be right here. 0, 0, 0. I don't know if I'll call it a vertex here, but the origin will be right in the middle of the saddle. And then this thing would have equation like z equals x squared over a squared, and then instead of plus, minus y squared over b squared. Hyperbolic paraboloid. Yes?
So for the hyperbolic paraboloid, that one is kind of sitting halfway through the xy plane?
Really, the way I've drawn it, so this axis, so this would be the origin right here. And this axis would have to be the x-axis. So imagine setting this guy equal to y equal to 0. Then you'd have z equals x squared over a squared, and you'd have this upward opening parabola as a trace. So yeah, I'd have to orient it so that would be the x-axis. An elliptic cone. So a cone in space, yeah, it looks like two ice cream cones stuck together at the sharp ends, right? So the way you would draw an elliptic cone, you could draw an ellipse, then a couple of lines from the left and right end of the ellipse, a couple of lines that cross each other, and then drawing a copy of the same ellipse below. It doesn't actually have to be the same. And remember, with the geometric cone, it doesn't stop here. It keeps going down forever, down and out, and kind of towards you forever. Likewise, it doesn't stop here. It keeps going up forever and ever and ever. Okay, so what would the equation of this thing look like? It would look like this. Z squared is equal to x squared over a squared plus y squared over b squared. And so if you compare it with, say, the elliptic paraboloid, it looks almost the same, except the exponent on the z is 2. So all the exponents are 2. Now, the origin would be right here in the middle. There's the origin, 0, 0, 0. And so that the z-axis would run, it would be the central axis of the thing, running down the middle of it like that. And if you interchange the role of x and z or y and z, it'll change the orientation. So this thing opens up with relation to the z-axis, right? But if you made the guy by itself on the left side, x squared, and then made this guy z squared, so just switch them, then it would tilt it, if the x-axis is coming out at you, it would tilt it, one end would open up towards you, one end would go through the wall.